Okay, let's start our lecture. The theme of our lecture will be the Laplace transform. And we begin with the basic definitions. So let us consider a complex valued function. Of a real variable f of t, where t belongs to real numbers, which satisfy the following conditions. The first one, f of t is a piecewise continuous function with possible discontinuous only of the first kind. Furthermore, it may possess only a finite number of discontinuous on any finite interval of the real line. Belonging and moreover, for any t, apart from the discontinuous points, we require that there exists a number a larger than 0 and a number h0 greater than 0 and some alpha belonging to the interval from 0 to 1 such that the following condition is fulfilled. For any h with the modulus lesser than or equal to h0. So, the second requirement imposed on the function f of t is that this function vanishes for negative t. And the third condition is that f of t grows when t tends to infinity, plus infinity, not faster than an exponential function. In other words, means that there exists a number m greater than 0 and some number s0 larger or equal than 0, such that the modulus of f of t is less than such a function when t is greater than 0. Then, definition. The minimum number S0 is called the index of rows of the function of t. Remark. In physical problem, as a rule, these conditions, the above three conditions, are satisfied. And as for this second condition, if the function f of t is not 0 for negative t, then one can always redefine the function in such a way. And this where Ct of t is the unit step function, and the right hand side of this expression vanishes for negative t. Where is this? 0. As for the second condition, I have already said, we can redefine the function as false. So, another one definition. The image of the function f of t, the Laplace as image of the function f of t, or the Laplace transform of the function f of t is called the function of the complex variable p which we can write in the algebraic form in terms of s and sigma, where s and sigma are real numbers. It's called the function of the complex variable defined as the definition of the Laplace transform. F large of p is equal by definition to the integral of such a form where f of t, f small of t, meets conditions above. besides this function, the function f small of t, is called the original function. And as I have already said, the function f large of p is referred to as the image of the f of t or the Laplace transform. Okay, let us consider the example. The example of Laplace transform. Laplace transform is a powerful tool for solving ordinary differential equations with constant coefficients, as we will see possibly at the end of this lecture or on the next lecture. But now we will consider the properties of this transform. So, the example, consider f of t, which is equal to the unit step function. Its value at the point t is equal to 0 is allowed for this definition because the contribution at this point is negligible. Then Laplace transform can be easily evaluated. Is equal 1 over p, where it assumes that the real part of p is greater than 0. In order that this integral be convergent. Okay, and this fact can be concisely written in the following form. Is transformed into 1 over p, and this sign means the Laplace transform. And in fact, we will always assume that the left-hand side in such type of expressions is multiplied by the unit step function. In our case, it is theta of t multiplied by 1. Okay, remark. The Laplace transform f large of p is defined by a formula star, which is written here, only in the half plane real part of p is greater than S0, where S0 is the gross index of the function f of t, f small of t. And as for other p, f of p is understood in the sense of analytical continuation. Which we discussed in the previous lectures. Okay. The theorem. For an original function f of t, the Laplace transform f large of p is defined in the half plane part of p is greater than S0, where S0 is the growth index of the function f of f small of t. And f large of p, that is the Laplace transform, is an analytic function in this half plane. The proof. In virtue of the property 3, of the original function f of t, the following estimate is fulfilled. The modulus of the Laplace transform is given by this integral. The modulus is given by the modulus of this integral, and we can estimate from above this expression using the well-known inequalities. That is, the modulus of the integral is less or equal to the integral of the modulus. Then we can write it is false. It is equal to the following expression, where at this point we used the following inequalities, namely we use the fact that the function, the original function, the modulus of the original function is lesser than an exponential function of such a form. And the second one is the fact that the modulus of the exponential function is equal to such an exponent, where we substitute the algebraic form of the complex number p and use the properties of the modulus. Then we will obtain such an expression, and this constant can be removed from the integral, and the integral is evaluated, and we obtain such an estimate. Thus we see the half plane, real part of p is greater than S0, the integral defining the Laplace transform is absolutely convergent. In order to prove analyticity of the function f larger of p in the half plane, in this half plane, I borrow the theorem from mathematical analysis, which was proved on that course, and the theorem states that if it states that if the integral I, which is by definition is given by such an expression, is uniformly convergent with respect to psi belonging to some domain D, besides such an integral, which is written here, is absolutely convergent in D. And the derivative of small depending on dxi with respect to psi exists, then the integral I is equal to the derivative of such an integral. In fact, this theorem states that under the fulfillment of this conditions, one can remove the derivative from the integral sign, or one can differentiate the integral with respect to the parameter psi. It is the same. Okay, let us apply this theorem to our case. And in our case, psi is p, and when p is greater than some s1, which is greater than s0, s1, yeah, have such inequality. We have such an estimate. In fact, this is the integral I in the formulation of the above theorem. And as for this integral, using the same reasonings as above, we can estimate it as follows. From above, this integral can be with respect to t can be readily evaluated, and we have expression. Therefore, the integral, this integral, is absolutely and uniformly convergent the domain u part of P greater or equal to S1 and which is greater than S0. Then applying the theorem, we imply that f large of P is differentiable, that is, it is analytic in the sense of theory of function of complex variables. The domain specified here. And since S1 is arbitrary here, but of course it must be greater than S0, then the function f of P is analytical in the half plane real part of P greater than S0. Thus the theorem is proved. So, the remark. It follows from the formulas formulated given in the theorem, the proof of the theorem, that Laplace, the modulus of the Laplace transform tends to 0 when s tends to plus infinity for any sigma, where s and sigma are the real and imaginary parts of this is a general property of the Laplace transform. It follows from these formulas. From this estimate, yes, we see that when s tends to infinity, then this tends to 0, and the modulus of this function tends to 0 as well. Okay, the next theorem. This theorem is called the inversion formula for Laplace transform. balance your formula. If the function f small of t is the original function, that is, it satisfies the properties 1 to 3, which we mentioned at the beginning of our lecture. And f large of p is its Laplace transform. Then, for any t where the original function f of t is continuous, we have the following relation. We have the formula for the original function f of t. It is given by the following integral in the complex plane. Where the contour of this integral runs parallel to the imaginary axis along the line. A real part of p is equal to a greater than S0 from bottom to top. And this integral is understood in the sense of principal value. In other words, f of t is equal to the limit when a large tends to plus infinity, and the integral is evaluated such limits. This is the formula, the meta inverse formula. The formula for inversion of the Laplace transform. And we see that the integration is carried out in the domain where the function f large of p is analytical, as it follows from the theorem above. This is along the line which lies in the half plane where the function f large of p is analytical. Okay, the proof. Let f tilde large of p is Laplace transform of small of t, which is given in the statement of the theorem. Which is given by this integral. In other words, f large t of p is defined by such an integral, which can be written as follows. Just substitute this formula into the definition of the Laplace transform. Now, due to the fact that the integral is absolutely convergent, we can change the integration order with respect to the variables omega and t. And as for the integral with respect to t, it can be easily related. And so we have the following formulas. Is absolutely uniformly convergent, as it follows from the theorem, as it follows from the previous theorem. For when real part of p is greater than 0, then can change the order of integration. Then we arrive at the following expression. Let me draw a picture. Our next task is to evaluate this integral. And let me draw a picture. Here is integration contour. This point A, this point S0, the growth index of the function f small of t. And there is some point P, and I draw an arc of a circle, gamma R large, and this is an arc of a circle with the center of the point at the origin, and with the radius R large. And so, basic idea how to evaluate this integral is to close this contour by this arc, and then apply the theorem about residues. And our task now is to prove that the integral along an arc, gamma R, tends to 0 when R large tends to infinity. So let us show this fact. Okay. This is the direction. The orientation is the contour gamma R, and the whole contour will be denoted as C. Okay. so modulus of omega is equal to r, and as follows from the theorem about the Laplace transform. The Laplace transform tends to 0 when the real part of omega tends to pass infinity for any imaginary part of omega. Yeah. As for 1 over e minus omega, it also tends to 0 when omega tends to pass infinity. That tends to infinity. And therefore, we have the estimate of the modulus of the integral along the arc gamma. We assume that r tends to infinity and omega can be written in an exponential form. So, under the modulus sign, we can rewrite this integral in the following way. For large r, we can neglect omega in this expression. Oh, excuse me, we can neglect p in this expression, integration with respect to omega, and just replace omega by this exponential form of a complex number. Then we have such an integral, and the integrand of this integral tends to 0, and the integral is carried out along a finite segment of a real axis. So, let's have r tends to 0 when r tends to infinity. The whole integral tends to 0 when r tends to infinity. Hence, we can write the original integral, that is the integral defining tilde f large, as the integral along a closed contour C, where r assumes that r tends to infinity, r large tends to infinity. Then we use the fact that f of omega is analytical function inside of this contour C. And apply the theorem about residues. The only singular point of the integrand is a point omega is equal to p, which is a pole of first order. And so we obtain comments here. Such inequality. As for this sign, this minus sign stems from the fact that the control C is run clockwise, that is in the negative direction, as we see from the picture bar. Okay. And so when we change the direction of the control C, this minus sign is. Okay, let us stop at this point. We have 5 minutes for the break. Okay, let's continue from this point. Thus, we see that f large tilde is equal to f large, and so we have proved this theorem. And now the theorem about uniqueness of the Laplace transform. If two continuous functions possess the same Laplace transform, then they are identical. The proof. As follows from the statement of the theorem, we have function f small of t is Laplace transformed into f large of p, and the function g small of t is also transformed, Laplace transformed to the function f large of p. Then, as follows from linearity of the integral defining the Laplace transform, we have that the difference between f small of t and g small of t is transformed into 0. It's clear from these formulas. Then, by using the Mellin's inverse formula, the difference between these functions is 0, and so these functions coincide. This proves this theorem. Okay. The next paragraph is called the properties of the Laplace transform. The Laplace transform has a number of interesting properties that allows one to find, for example, to find the inverse Laplace transform not by using the Mellin inverse formula, but by using all these properties. And I'll show you the example of such usage of these properties. So First we introduce a notation. The original function of the Laplace transform will be denoted by small letters. For example, f small of t, g small of t, and so on. And by large letters, we will denote the corresponding Laplace transforms, the images, Laplace images. That is large of p is equal to such an integral. And this large formula we will briefly denote as I have already mentioned by such a sign. Course, Laplace transform by this formula. On the first part of our lecture, I showed that the Laplace transform of the step, the unit step, is the function 1 over p. And I remind you that it is always assumed that the left-hand side in the expression of such a form is multiplied by the unit step function. It is also clear that the exponential function is transformed into such an expression when u part of p is greater than u part of p0. The proof is elementary, namely we consider we must consider the full integral and it is written as follows. It is equal 1 over p minus p0. Besides the particular case of this formula, such an exponent is transformed into p minus I times omega. Okay, let us turn to the properties. The first property, which is evident and in fact it was used in the proof of the previous theorem, is linearity. The Laplace transform is written as given as this formula, namely a linear combination of originals is transformed into linear combination with the same coefficients of Laplace images, the corresponding Laplace images. The alpha and beta are arbitrary complex constants. Cool. Follows from the properties of the integral. So, simple application. Let's finish some simple applications of this formula. of this property. Let's consider the Laplace transform of the sine function. Of course, it is written as the Euler formula in such a form. And then we know the Laplace transform of these two exponents, and using linearity of the Laplace transform, we conclude that it is equal to such an expression. Which is simplified to this formula. And as for cosine function, by applying the same procedure, we find that is equal to such a linear combination. Taking these terms together, we have such a formula. Hyperbolic sine function is Laplace transformed to such a formula, such an expression. And as for hyperbolic cosine function, its Laplace transform is written as follows. Okay, the next property. Similarity. It is a theorem or property about the Laplace transform of such an expression. It says that it is equal to 1 over alpha times f depending on p over alpha. There we assume that alpha is greater than c. Proof. By definition, if you consider the Laplace transform of such a function, such an argument, it is specified by the integral of such a form. Then we just stretch the integration variable by 1 over alpha, and we can have the integral of such a form, and this integral is just the Laplace transform of the function f small of t, but with the argument p over alpha. So the property is proved. The third property, the derivative of the original, or the derivative of the Laplace transform. This property says how to differentiate easily image of the original. Okay. if the function small of t is continuous, it will be the derivative of the original function. The original. The next property will be about the derivative of the Laplace transform, but now we'll prove the theorem about the derivative of the original function. If the function f of t is continuous, for positive t, and its derivative is the original function, that is, it satisfies all the properties that all the three properties that were given in the beginning of our lecture, then its Laplace transform is given by the following formula. And as for higher derivatives, we have the following statement. The nth derivative of the function f of t is the original function, then this nth derivative is transformed into such an expression. Where the derivative of f small function are understood from the right. Understood to be taken from the right. Such a formula should be satisfied. The proof. By definition, consider such an integral. F prime of t is the original, so this integral is well defined. And we can integrate it by parts. Integrating it by parts, we arrive at the following expression. Then this entity is equal to this formula. The real part of p is greater than 0. As for this expression taken as the upper limit, we have the estimate. The modulus of this expression is lesser than such an exponent. We have already used such an estimate when we prove the theorem about the Laplace transform. Here, as 0 is a growth index of the function f small of t, and so this is the real part of p, And so when s is greater than s0, the modulus of this expression tends to 0 when t tends to infinity. And so, we have already used this fact when we neglect the contribution of the upper limit of this expression, because it is 0 when 0 part of p is greater than s0, which is assumed here. And as for higher derivatives, we consider the case n is equal to 2, then we can just apply the formula for n is equal to 1 to the first derivative of the function f of t, which is right, the second derivative as a derivative of the derivative. And then applying the above formula, this false. We apply the above formula, but we know that the image of f prime of t is equal to such an expression. So we have the general formula for n is equal to 2. And so one can prove this formula for arbitrary n. The proof of the property is finished. Remark. In this particular case, when small f taking the point 0 is equal to 0, the formula above is simplified to such an expression. As we see that the derivative of the original is transformed into a multiplication by p, but of course only in this case. And if this is not the case, then the additional terms appears on the right hand side of this expression. And the fourth property, derivative of the Laplace transform. The following formula holds. It says that minus t to nth power multiplied by f of t is Laplace transformed into nth derivative of the Laplace image. So, the proof. the integral, the Laplace integral, of p, which is given by definition by such an expression, and its derivative, and its derivatives are uniformly convergent. In the half plane, u part of p is greater than s0, where s0 is a gross index of the function f small of t. So the theorem above. And hence, we can differentiate this integral with respect to the parameter p and derive the formula. Differentiation can be easily performed. It's just a derivative of an exponential function. And so on. Thus, the theorem is proved. We see that this function is Laplace transformed into f prime of p, f prime of t. This function minus t to second power times f small of t is transformed into the second derivative of the Laplace image, and so on. Thus we will have, in general cases, in the case of nth derivative, we have such general formula. Example. We know that unit step function is Laplace transformed into 1 over p. Then we can differentiate the Laplace image n times, and by using the general formula from this property, we obtain such a relation. And differentiating this ratio we have such a relation, and multiplying this equality by minus 1 to nth power, and using the linearity of the Laplace transform, we have relation. The t to nth power is Laplace transform to factorial of n over p to nth plus 1 power. Another example. Consider the Laplace transform of the exponent. You know that it is equal to 1 over p minus p0. Therefore, using the same arguments, we conclude that the former relation holds full formula. The Laplace transform. Integration of the Laplace transform. This property says that the following formula is valid. Not Laplace transform. Again, integration of the original function. Consider the Laplace transform of this definite integral, then it is transformed into such expression. That we see that the integral is transformed into 1 over p. And I remind you that the derivative is transformed by the Laplace transform into p and some additional terms when f of 0 is not equal to 0. And here we see that the integral and the derivative are the inverse operations to each other. So the proof, if f of t is the original function, then it can be easily proved that its definite integral of such a form is also an original function. These all three properties which were stated in the beginning of our lecture are satisfied by this function. In fact, it follows from the observation that integration of a function improves its properties, improves its smoothness, and so on. And besides, we see that this function, this integral, is 0 at when t is equal to 0. Use the notation. G of t is by definition this integral, and we see that it is equal to 0 when t is equal to 0. Then the Laplace transform consider the Laplace transform of g small of t and denote this Laplace transform by g large. And by the formula of for derivative of the original function, we have obviously have that f small is equal to g small prime. On the other side, applying the formula for the derivative of the original, we have such a general expression, and using the fact that g small of 0 is equal to 0, and we have this one expression, and this expression must be equal to f large of p, because it is just a Laplace transform of f small of t. Therefore, g large of p is equal to f large of p divided by p. The proof is finished. The sixth property. Integration of the Laplace transform. The integral such a form is convergent. Then it is the Laplace transform of the function f small of t over t. In other words, we have such a relation. Where f large of x is a Laplace image of the function f small of t. The proof. We have the following relation. Let us substitute the definition of f large of x in the Laplace transform. It is given by the formula integral. Then we change the integration order. It is justified because the integral is absolutely convergent. And then we have then the integral with respect to x is easily related. It is equal to 1 over t. And so we see that this function f small over t is Laplace transformed into this function. Thus, the theorem is proved. sign order. The change of integration order is justified because this integral is uniformly convergent. For example, of application of this property. Let's consider the difference between two exponential functions. And as we know, by linearity of the Laplace transform and the formula that we already obtained, you know that it's Laplace transform, the Laplace transform of the left-hand side is equal to such a linear combination. Then we integrate the right-hand side of this expression and apply the previous theorem. Then, as for the left-hand side, we just have to divide this expression by t. And as for the right-hand side, we must evaluate this integral. This integral can be really evaluated. And we arrive at the logarithmic function, such form. Okay, the next property. Theorem's property, Theorem, or another name of this property, T-shift translation rule, T-shift rule, or T-translation rule. It says that the Laplace transform of the function such form with shifted t argument is given by the following expression. Proof this statement, and let us take into account the obvious fact that the function on the left-hand side, the original function, is equal to 0 when t is less than tau. Then have such a relation. By definition, the Laplace transform we can write in the following way. Then we shift the integration variable by tau, and we have a simple integral of the exponential function multiplied by f of t, and So eventually we can write this integral the following way, and by using the definition of the Laplace transform as f small, we have such a formula. Thus, the property is proved. So let me stop at this point, and that's it.